Exercise 4.32a. Show that homeomorphism preserves interiors, as indicated in the following implication. If f from x to y is homeomorphism, then f of the interior of A equals the interior of f of A for every A in x. Alright, well, before we dive in, I wanted to point out that this equality here is not necessarily true if you just assume that f is continuous. Okay, it's not a strong enough assumption. And well, here's an example of why. Consider the function f from r to r, which just takes every real number and maps it to 0. So geometrically, it's taking the real line and it's collapsing it down to a single point. And well, let's think about what two sides of this equation would be in this case. Right? And let me take A to be equal to R. Okay, so it'll be the whole domain. All right. Well, in this case, the interior of A is the interior of R in R, which is all of R. So we have that, and if you apply f to that, you get f of r, which is just 0, right? The second system, just a 0. Now, what if we do it in the other order? Okay, what if we start off with f of a, which certainly gives us just 0, and then we look at the interior of that as a subset of R here, right? Well, that's an isolated point. It doesn't have any interior. Its interior is the empty set. Okay, so you see that in this case, for a function which is certainly continuous, it's a constant function, right? All constant functions are continuous. We have that the interior of f of a is actually smaller than f of the interior of a. Okay, so we're not going to be able to prove one inclusion in that case. But it turns out we can prove the other. All right, so we're trying to prove that if f is a homeomorphism, then we do have an equal sign here, and so I'm going to prove that each side is contained in the other side. Okay, and let's first use continuity of f to prove that, well, it's whatever is true here, right? That the interior of f of a is always a subset of f of the interior of a. Okay, well, the fact that f is continuous means the preimage of an open is open. And so do we know any open sets in the target? We sure do. The interior of f of a. So since the interior of f of a is open in, well, okay. Remember, we're doing a function from x to y, so open in y. Its preimage, which would be written f inverse of the interior of f of a, is open in x. Okay, that's what continuity means. And well, I'm almost there if I could show that this was a subset of the interior of A. Okay, and to do that, I know it's open. I just have to show it's contained in A. And then I'll know that it's also contained in the interior. Why is this in A? Well, we can get that by applying the function f inverse to, remember f's invertible, to both sides of this equation, which I know is true, the interior of f of a is certainly a subset of f of a. Right? Every interior is contained in the set itself. And then after we apply that, we're going to cancel. Okay. And that's going to give us, copy it from up here. Right, applying f inverse to the left side gives us this thing we're interested in. And that's interesting. And applying f inverse to the right side gives us f inverse of f of a. And that cancels to a. Okay, so this set is definitely a subset of A, and it's open, and therefore it's contained in the interior, right? Because the interior is the union of all such open sets contained in A. So it follows, by definition of interior, that we modify this one that this is a subset of the interior of A. Okay, and that's almost what we want, right? We just have to apply f now to both sides to cancel this f inverse and get an f over here. So applying f to both sides and canceling again, which we can do because, again, these are invertible functions. If we were just using preimage notation, you have to be a little more careful about canceling. Okay. We get that our desired inclusion holds. Whoa. There we go. Okay, so we're halfway there. And the good news is we can kind of cheat by using what we know to get the other direction. Okay. So if we used continuity of f to prove this inclusion, remember, f's a homeomorphism, so f inverse has to be continuous as well. So we're going to use the continuity of f inverse to get the other inclusion. Okay. Since f inverse is also a continuous function, bijection, we have that, well, I'm going to use what I just proved, right? That this statement is true with f inverse in place of f for any set B and Y. Okay. So an interior of f inverse of B is a subset of f inverse of the interior of B for every subset B of Y. Okay, and now I just kind of need to change these f inverses to f's, and then magically the right thing is going to appear. So to deal with the f inverse on the inside of the parentheses here, I'm going to say applying this in this special case where this b and y is actually f of some a and x. Okay, in the case where b equals f of some subset a of x, well, what happens? Okay, on the left we have interior of f inverse of f of a, and those cancel, and we just have interior of a. And on the right side, we just replace b by f of a. And we get a little bit messy, f inverse of interior of f of a. Is it the right number of parentheses? 1, 2. I think it is. Okay. All right. And then also need to deal with this f inverse, and for that we can just apply f to both sides. Okay. So applying function f to both sides yields f of interior of a Here's a subset of, okay, and then f of this side will just cancel that f inverse. And, oh, something funny's happening with parentheses there, that's okay. Let's try and fix that. Interior f of a. Okay, good enough. So we're done. We've shown that int of f of a is contained in f of int a, and vice versa. Therefore, those two sets are equal in the case when f is a homomorphism.